Hello, this is Unit 6, Day 4. Unit 6 is our unit on exponents and radicals, and our fourth day we are talking about simplifying radicals. So I'm going to have you pause the video while you complete this chart. It will be helpful for you to have this chart completed while you're working on these problems. These are just perfect squares, so a quick reminder. Perfect squares are called perfect squares because if you have, for instance, 3 squared, it means you have 3 to the side and 3 up and down, and it makes a perfect square. You have the same lengths on each side. This is a 4 by 4, or 4 squared, this is 5 squared. So if we have a perfect square, it means that if we were to take the square root of it, we would get an integer. So 1 squared just means 1 times 1, which is 1. 2 squared is 2 times 2, which is 2, and so on. So please go ahead and complete these. I hope that you have them memorized up to at least like maybe 15 squared. It's helpful to have them all memorized, or at least roughly memorized, so that you can recognize a perfect square when you see it. So pause the video now, complete this, and I'm just going to complete it and not hold up the video time. All right, so here's our completed table. And using the Texas Instruments 30 school calendar, what is this? A calculator, school calculator. Here's how you can find the square of a number. So if I wanted to know 15 squared, I type in 15. I can use this button x squared, and that will immediately give me 15 squared. Or I can say that I want to know 15 raised to the power of 2. So 15 is my base. I'm going to use this button, y to the x, to say I want the base raised to the power of 2, and I tell it that 2 is the exponent, and I say equals. All right, so I'm glad that you have that table figured out. We were squaring all of these numbers, so 5 squared means 5 times 5, which is 25. So if I have a number and I want to undo something squared, I'm going to take the square root of it. All right, so the square root of a number is whatever value you get, so that when you multiply it by itself again, it gives you back that number. Okay, so the square root of 9 is 3, because when you multiply 3 times 3, you get 9. So the square root of 9 is written this way, square root of 9. And the value of that amount is 3. That's the same information. Okay. I use this little checkbox looking thing. It's called a radical. That's the symbol that I use to show that I'm going to do a square root or a cube root or any root of some number or expression. And the word radicand right here, that's the number underneath that symbol. Okay, so here's some fancy information about the root of a number. So this circle over n, this is actually the index. So normally when we're taking the square root, like when I said the square root of 9, there was no number in that little checkbox. So if there is no number at all, you assume that it is an index of 2. There's a little invisible index of 2 there. What times itself 2 times is going to give me 9. Okay, so when I'm talking about the cube root of a number, I will see a number. What times itself 3 times gives me 8. So I don't want to know what times itself 2 times gives me 8. I want to know what times itself 3 times gives me 8. And that is the number 2, because 2 times 2 times 2 is 8. Or I can say 2 cubed is 8. Notice how I'm saying 2 cubed is 8. That is no longer using the square root or cube root symbol. Okay, so the square root of 9 has an invisible 2, and I know the square root of 9 is 3. I know that 3 squared equals 9. So I jumped ahead just a little bit by jumping to our cubes and cube roots, just to point out that that index does exist and we do care about it. Okay, so the checkbox looking thing is called the radical. And the number that I'm going to take the root of is called the radicand. radicand. And again, if there is no index at all, there's no number in that checkbox, we assume that that number n is 2. All right. If a radical has more than one root, which is possible with positives and negatives, if we just ask for the square root of a number, we just want the principal root, the positive root. Okay, so to be fully simplified, a radical should have no perfect squares left inside, because if you leave a perfect square inside a radical, you're leaving math for your math teacher to do, and we don't want to do that. Okay, also, so no perfect squares as factors underneath there, and no fractions in the radicand, and no radicals, so no square root or cube root or any root in a denominator, no radicals in a denominator. So more rules for you. Let's take a look. We're going to do some of these problems just following rules. Okay, so what we were just looking at on the other side of this page was a whole bunch of perfect squares. So you take the square root of a perfect square and you just get an integer. Okay, most of the time we're going to get numbers. There are far more numbers that are not perfect squares. So we're going to try to simplify those numbers that are not perfect squares. And so what we can do is we can use rules like this one, the square root of a times b, where the radicand is a times b, can be broken up so that it is the square root of a times the square root of b. We assume that a and b are both greater than or equal to 0. They're not going to be negative. Okay, and so we might do this because when we're trying to find our simplest form, we're going to try to find any factors of a radicand that are perfect squares so that we can take the square root of them, get them out of there. All right, so an example is the square root of 50 here. Well, looking at the square root of 50, that's not a perfect square. So if I put 50 in my calculator and hit the square root button, it gives me a decimal. Okay, that's not what I want. But I want to think about, what do I know about 50? 50 is 25 times 2. And the reason I care about that is I know 25 is a perfect square. So if I have this rule up here that says the square root of a times b can be broken up into two different square roots, that's what I'm going to try to do. Okay, I'm going to break up 50 into 25 times 2. It's the same amount, but I know that I'm allowed to have lightning strike and split that apart. So it's really the square root of 25 times the square root of 2. That's the same as the square root of 50. The reason I did that is I know that the square root of 25 is 5. So I just did some math that I could do. So my answer to what is the square root of 50 is, it is 5 times the square root of 2. Okay, this one was pretty easy because 50 pretty much is 1 times 50 or 2 times 25. And so it was easy to figure out which of those factors was a perfect square. It's not always that easy. It's not always that completely evident. So I'm going to show you another way that we might look to break up a radicand and find a factor that is a perfect square. All right, so I'm trying to, there. So this is using the prime factorization process. So we're just going to find all the prime factors, or find a factor tree is probably what you would have called this before. So what we're going to do is take our number and break it into factors. So I know 50, it's even, so it's divisible by 2, right? So 2 times 25. Okay, 2 is 2 times 1. As soon as I get to that prime number that can only be multiplied by 1 in itself, then I'm going to leave it. So that's why we have a circle here. That's a prime number. Okay, 2 times 25. But I know 25 is 1 times 25, or it's 5 times 5, right? Okay, so just thinking about that 1 times 25 or 5 times 5, I'm going to break it up into 5 times 5. 5 is a prime number, and so I've got those prime numbers in circles. We're not always going to use the circles to show you. I'm just showing in this example here. All right, so my prime factors are all of these guys. 2 times 5 times 5. If I multiply that all together, it's 50. 2 times 5 is 10, times 5 is 50. Okay, but look, I have a pair. if you're taking the square root, remember the square root of 50, there's really a hidden 2 here. So I'm looking for pairs, things that come in 2s. If I found a pair, I can pull one of the pair out of my radicand. I can pull it out from underneath that radical. Okay? I have 50 is 5 times 5 times 2. I have 2 5s right here, 5 times 5. I'm going to pull those guys out of the house. I'm going to take the square root of 5 times 5. Square root of 5 times 5 is the square root of 25. So when I take the square root of 5 times 5, it is just 5. Okay? The square root of 5 times 5 becomes 5. And it's still times the square root of 2, because I still had that, right? And so 5 times the square root of 2 is my final answer. We got that here, and we got that when we used our other method as well. Okay, so let's take a look. I'll do some of these with prime factorization and some of these just using the product rule, okay? So I know that 24, I can think of 24, it's 2 times 12. Well, neither one of those is a perfect square, so I don't really, It's 3 times 8, no perfect squares there. It's 4 times 6. Aha, I like that because 4 is a perfect square. So I'm going to rewrite this as the square root of 4 times 6. Okay, the reason I did that is now I can break this apart with my product rule, and I get the square root of 4 times the square root of 6. I did that because I know the square root of 4 equals 2. 2 times the square root of 6 is my answer. Okay, and I know I got all the way down because 6 can only be 3 times 2 or 1 times 6, and that's all. Those are all prime factors. All right, for 72, let's break that one down using our factor tree. Okay, I know it's even, so I'm going to say that this is 2 times 36. Okay, 2 times 36. So 2 is prime, I'm going to leave that there. 36, I could say it's 2 times 18, or I could say it's 3 times 12, or 4 times 9. I can do anything I want. I'm going to go ahead and stick with my 2's, but I promise if you were to choose a different factor, by the end you're going to come up with the same tree as me. This is going to be 2 times 18. 2 is prime, so I'm going to leave that there. 18 is even, so I know it's 2 times 9. 2 is prime, so it's going to stay there. And then 9 can either be 1 times 9 or 3 times 3. I'm going to break it into 3 times 3. 3 times 3. 3 is prime and 3 is prime. Now remember, we said with a square root, there's an invisible 2 right there. So I'm looking for things that come in 2's. That's what I'm going to pull out of the house. Okay, so I'm going to pull a pair of 2's out, and I'm going to pull a pair of 3's out. They get to go outside of their little radical house, and this 2 here, he doesn't have a pair, right? He's all by himself, so he's going to stay in the house. Here's what this is going to look like. It's really the square root of 2 times 2 times 2 times 3 times 3. Okay, I have a pair and I have a pair. If I have a pair, I get to pull the pair out and leave just one of those guys on the inside. Or we can break this up into 3 different sections here. This is going to be the square root of 2 times 2 times the square root of 2 times the square root of 3 times 3. That might be easier to see what we're talking about with our pairs. So square root of 2 times 2, if 2 times 2 is my radicand, I'm going to pull one of those 2's out, right? It would be the square root of 4, or it would be just 2. The square root of 2 times 2 is 2. The square root of 2 I can't simplify, so that's going to just still be the square root of 2. But the square root of 3 times 3, I'm going to pull one of those 3's out because the square root of 3 times 3 is just 3. Okay, 2 times the square root of 2 times 3. I'm going to simplify that. I can multiply 2 times 3 and I get 6. And the square root of 2. That is my answer. 6 times, oops, you can't see it, sorry. 6 times the square root of 2. Okay, I'm going to do this one a whole different way just because I really want you to see that there are ways to do this. All right. So if I'm thinking about 72, I remember that 36 is a perfect square. So I'm going to come over here, and it's a decently sized one, right? So I'm going to say 72 divided by 36. I'm just curious. Look at that. So 72 divided by 36 is 2. So I can break 72 into 36 times 2. I'm allowed to do that. Why would I do that? Well, this is pretty cool because 36 is a perfect square, right? I know that 36 is 6 times 6. I know the square root of 36 is 6. 2 is already a prime number, and 6 is prime, 6 is prime. So if I take the square root of 6 times 2, I can break it up. I have the square root of 6 times the square root of 2. And I know the square root of a pair of things multiplied together is just one of those things, right? This is 36 under there. The square root of 36 is 6 times the square root of 2. That is my answer here. That's the answer we got before. Sorry, that's the answer we got before. So there are many ways to solve these problems. You can solve them by just looking for a square root to break up, or you can find that factorization tree. And there are probably many ways people describe this too. All right, I'm still working with square roots, and I have the square root of 16. Well, in my head, I'm thinking to myself, 16 is a perfect square. So let me try something. I'm going to say that this is the square root of 16 times 10. Okay, and that's just because I happen to realize 16 is a perfect square. If I do that, I'm going to break it up into 16, the square root, times the square root of 10. Square root of 16 is 4, so I have 4 times the square root of 10. Now, I might, hold on. All right, I'll try to finish up these two problems and end this video, and then we'll start a second video on the rest of the notes. Oh no, this is the end of the notes. I'll try to finish up these two before my overhead announcements keep coming. Okay, 4 times the square root of 10. I want to make sure the square root of 10 is as simple as it can be. So I just want to think about, is there a perfect square that's a factor in there? So here's 10. 10 is 1 times 10. It's 2 times 5. There are no other factors, and so I don't see any perfect squares in there. So I'm going to say that this is good. It is my final answer. Square root of 48. I can break that up. I know 4 is a perfect square. But I also know 16 is a perfect square, so 16 times 3 would work. So let's do this one with a factor tree, okay? Just to make sure we can find all of the pairs of numbers. 2 goes into 48 24 times. 2 is prime. 2 goes into 24 12 times. 2 is prime. 2 goes into 12 6 times. 2 is prime. And 6 comes from 2 times 3, right? So we're going to say 6 is 2 times 3. Those are my prime numbers there. Now I'm looking for pairs. So if I write this out, it's going to be the square root of 2 times 2, that's these guys, times 2 times 2, that's these guys, times 3. Now I'm looking for pairs. I'm going to pull one of these guys out. They both are coming out actually, and I'm just going to have 2 on the outside, times one of these guys, so that's times 2 again. And then square root of 3 is, he's done. He has to stay in the house. He doesn't have anybody that he's paired up with, okay? All of these things are being multiplied together, right? So 2 times 2 is 4, and I have 4 times the square root of 3 as my final answer. And again, there are lots of ways that these are being described, so feel free to check in with me if you have additional questions.